Hello, welcome to week 8 of the ECE9013 course. In this week's lecture, we will be discussing how to measure orders of growth of algorithms, the big O notation, complexity classes, and complexity class examples. Starting off with a discussion of why we need to do this. Computers are becoming faster and faster. However, the data that's being collected is also growing. For example, in 2014, Google served more than 30 trillion pages covering more than 100 million gigabytes. So imagine having to search all of these documents or data. Therefore, simple solutions may not scale well enough with size in an acceptable manner. So how can we decide which option for a program is most efficient? That is, computationally speaking, how can we decide if the algorithm is good enough for the particular problem that we are tackling? Note that we need to separate between time efficiency and space efficiency of a program, because there's a trade-off between them. You can perform some computations in a time-efficient manner, however, it would require large amounts of space, and the opposite would be true. For example, we can sometimes pre-compute results and store them, and then use the lookup option to retrieve them. In this lecture, we will only be focusing on the time efficiency. Now, there are many challenges to understanding the efficiency of a solution of a computational problem. This is because a program can be implemented in many different ways, and there are multiple potential algorithms to solve a problem. We would like to separate the choices of implementation from choices of more abstract algorithms. Therefore, to evaluate the efficiency of programs, we have different potential methods, such as measuring with a timer, counting the number of operations, and an abstract notation of order of growth. So starting off with the most basic way, which is timing a program using the time module, we initiate the clock before we call the function. We call the function and then we stop the clock. So this would give us an estimate of the time needed to perform the function. However, although this would give us the time for the function to run, timing would be inconsistent because it can vary based on the implementation, and it can also vary depending on the computer being used. Furthermore, it is not a predictable measure, especially if the input is small. So time varies for different inputs, but it cannot really express a relationship between the input and time. The second potential way to measure the efficiency of a program is to count the number of operations. So assuming that each step takes a constant time, such as mathematical operations and comparisons and assignment, all of these we can assume that they take a constant time. We can count the number of operations executed to get an idea about the efficiency of the program. However, this is still not what is desired because the counting depends on the algorithm, and it also depends on the implementation. And although it is independent of the computer, there is no clear definition of which operations to count. So count actually varies for different inputs and can come up with a relationship between inputs and the count. However, there's still some ambiguity as to which operations to count and which operations we can ignore. That's why we still need a better way. This is because timing and counting evaluate the implementation, and timing evaluates the machine. However, what we want is to evaluate the algorithm independent of the implementation or the machine applying it. We would like to evaluate scalability, and we would like to evaluate in terms of the input size. So we are still going to focus on the idea of counting operations, but we don't have to worry about small variations. For example, whether a particular operation takes 3 or 4 primitive operations. We are going to focus on how the algorithm performs when the size of the problem gets arbitrarily large. And we want to relate the time needed to complete the computation against the size of the input. Therefore, we need to decide what to measure, given that the actual number of steps may depend on specifics of the trial. Hence, we would need to choose which input to use to evaluate a function or a program. We would like to express the efficiency in terms of the size of the input, so we need to decide what the input is. The input can be an integer, it could be a length of a list, it could be any other metric. So we need to decide which parameters are given to the function and how we can relate the implementation of the function or program to these inputs. For example, assume that we have a function that searches for an element in a list. If the element we're looking for is the first element in the list, this is the best case because we would need only one operation. The worst case is if the element is not in the list, because we would have to traverse all of the list to determine that. When we look through about half of the elements in the list, this is what we call the average case. So we want to measure this behavior in a general way. Suppose that we have a list L of some length L. The best case, which is the minimum running time over all possible inputs, is length L, which is basically having the element being the first element in any list. The average case is the average running time over all possible inputs of a given size, which is the length of L. And the worst case, which is the maximum running time over all possible inputs, would be linear in the length of the list. So if the length of the list increases by 1, then the order will increase in a linear manner. So we would like to be able to measure this order in a generic manner. Thank you.